Good morning, everyone. Um, my name is Auwal Bala Abubakar. Today I'm going to give a seminar which is part of the PhD seminar series. And the title of my talk is New Three-Term Conjugate Gradient Algorithm for Solving Monotone Nonlinear Equations and Signal Problems, Signal Recovery Problems. The outline of my talk is divided into four. First, I will give a brief introduction. Second, I will propose the algorithm together with its convergence. And the third outline is going to be the numerical experiment, which is divided into two. First is going to be a numerical experiment on some benchmark convex constrained nonlinear monotone equations. And then the second experiment is on signal recovery. And finally, a conclusion will be given and some references also at the end of the talk. The introduction. So in this work, we consider finding a vector x, a subset of Rn, x in omega subset of Rn, such that f of x is equal to 0, where this function f is a function from Rn to Rn, and is assumed to be continuous and monotone. And omega is a closed convex subset of the equivalent state Rn. By saying the function is monotone, it means the function satisfies inequality 2 for all x, y in Rn. This inequality holds. Now, if the system given in equation 1 is monotone, that is the function f is monotone, in the system given in 1, then we refer the system 1 as a nonlinear or a monotone nonlinear equation. There are several iterative schemes for solving such type of problems. Over the years, there are immense attention in order to solve this kind of a problem. Why? Because it arises in many applications. Example of such applications are it arises in the ballistic trajectory computation and vibration systems, which can be found in reference 13. It also arises in the power flow of equations. It also arises in economic equilibrium problems, and it also arises in the signal and image recovery problems, which is the area which we are more concerned on. Now, like I mentioned also, there are several methods for solving such kind of problem. Some of the famous methods are the Newton's and the quasi-Newton method. But in this context, due to assumption of the function f, the function f is monotone and Lipschitz, not necessarily differentiable. So in that regard, the Newton and the quasi-Newton method may not be appropriate to solve this kind of problem, because when using the Newton method, function under consideration needs to be continuously differentiable. But in this case, our assumption is that f is just monotone and which is continuous. So Newton method may not be appropriate in handling this kind of problem. So that is why another method which does not require the differentiability assumption has to be employed. And in this regard, we consider the conjugate gradient method. And the conjugate gradient method is one of the strongest and efficient methods for finding solution of one, because it is characterized by simplicity, that is very simple to implement, and its ability to solve large-scale problems. Why? Because in Newton's method and quasi-Newton method, there is need to compute and store the Jacobian matrix at every iteration. So when the dimension of the problem becomes very large, the Jacobian matrix also becomes very large. And computing such kind of matrix and storing it at each iteration is going to be very, very difficult. So, but in the case of conjugate gradient algorithm or conjugate gradient method, it does not require computing or storing of Jacobian at every iteration. In fact, it is matrix free. It doesn't require an n by n matrix at each iteration. What it requires is an n by 1 vector at each iteration. So you deal with n by 1 matrix, or you can say n by 1 vectors. So the conjugate gradient method works like this. It generates sequence of iterations or sequence of iterates xk using the formula given by 3, which is xk plus 1 is equal to k plus alpha k dt, where k is starting from 0, 1 to up to where the iteration stops. Alpha k is the step size, and dk is the side direction. The step size is usually obtained using a suitable line search procedure, which we are going to see later in the algorithm. And the direction dk is given by 4. So when k is 0, dk is minus fk. So d naught is just minus f naught. And when k is greater than 0, that is from 1, we have minus fk plus beta k dk minus 1. Beta k is called the CD parameter, and fk denotes the function evaluation of f at the point xk. Now, this parameter beta k is what differentiates between any two CD methods. So when you have a new parameter beta k, then you have a new conjugate gradient direction. And when you have a new conjugate gradient direction, then you have a new conjugate gradient method. So this beta k is very crucial. And this beta k is going to be, most times, is going to be the point of concentration. In particular, in this work also, we are going to see that we are going to define a new beta k, which makes us to derive a new direction, conjugate gradient direction, and by implication, we have a new conjugate gradient method. That is why we call it a new conjugate gradient method. And as for the 3-term, we are going to see why it is 3-term subsequently. Now, throughout this work, we assume that we assume the following. The first is that the solution of the problem 1 is not empty, and we denote it by omega prime. A2, the second assumption is that f is monotone, which we already mentioned that the function needs to be monotone. And A3 is that the function is elliptic continuous, meaning it satisfies the inequality below. And finally, unless the solution is obtained, we assume that fk is not 0, meaning function evaluation of f at xk is a non-zero vector unless the solution is obtained. Okay. Now, the paper or our working paper or the paper we're interested in, or we derive our motivation from, is the paper by Zeng and Zeng. In this paper by Zeng and Zeng, they propose 2 new Diliau conjugate gradient methods for solving unconstrained optimization problems. I did not mention this earlier. The conjugate gradient method is used to solve unconstrained optimization problems, and at the same time, it can be used to solve nonlinear equation, general nonlinear equation. But in this case, we are considering nonlinear equation where the function under consideration is monotone and lattice. So Zeng and Zeng, they propose the 2 new Diliau. Diliau is a famous conjugate gradient parameter beta k. So they propose a new Diliau-like, meaning it's like a modified version of the Diliau conjugate gradient parameter. And by implication, they derive a new direction, which they use to solve an unconstrained optimization problem. The function f, small f, is from Rn to R. This is a mistake. It's a typo. is supposed to be from Rn to R, not from Rn to Rn, and is a continuously differentiable function. Now, the proposed algorithm by Zeng and Zeng have the following search direction as, or have the search direction defined by Zeng and Zeng is given by 5. So they define dk when k is 0 as minus d of xk, and when k is greater or equal to 1, they define it as minus d of xk plus beta k dk minus 1, where g of xk is nothing but the gradient of small fk, where small fk is the gradient of f at xk, and beta k is the conjugate gradient parameter. So we can see that when considering solving an unconstrained optimization problem, the direction given by 5 will contain the gradient of the small function to be minimized. While,
sorry, Mr. Auwal. Mr. Auwal.
Yes.
Sorry, I need to.
I cannot hear you. Your mic is off, I think.
Can you hear me?
Yes, I can hear you.
Okay, sorry for interruption. I have a question. How do you define that minimum? You said the minimum of fx, x belongs to Rn. Because the value of fx is coming from Rn. So how do you define its minimum? What do you mean by this minimum?
You are trying to find the vector for which this function f will attain its minimum.
Okay, the
minimum value.
Okay, minimum value in Rn, right?
No, that's why I corrected. I said that function is from Rn to R, not from
Rn to
Rn.
Okay. That's why.
I made mention like, yeah.
Okay,
yeah.
That makes sense. I got it.
Yeah,
please go ahead. Sorry.
Okay. Thank you.
No problem.
Okay. So in this work by Zeng and Zeng, from this direction, we can see that they have the conjugate gradient parameter beta k. So they define two beta k's. The first one is the one given by 6, which they call beta k superscript DHSDL. And another one they define where yk is given by gk minus 1, which is the difference of the gradient, previous and the current gradient. And mu present in 6 is given the condition that it has to be greater than 1, and the t also should be greater than 0. Now also in the 17, another conjugate gradient parameter beta k is introduced by replacing yk minus 1 in 6 with gk minus 1. So if you replace yk minus 1 in 6 with gk minus 1, and also using the negative term minus dk minus 1 times with dk minus 1, you will get another beta k defined by 7, which they call beta k dl SDL. Now in this paper, they were able to show that the algorithm converges globally, but under the strong Wolf-Line search. And they show also that numerically it performs very good. Now this is the paper we are motivated by. Now, another motivation is that in the paper reference 10, Kurapetse and Kylo modified one of the conjugate gradient parameters defined by Zeng and Zeng, which is the one given by 7, that is the last one, not the one given by 6. And they proposed a new conjugate gradient-based projection method for solving problem 1. However, in this case, they consider omega to be the whole of Rn. So it's not a constraint problem. So in this case, Kurapetse and Kylo considered an unconstrained problem where omega is the whole space Rn. And they define the search direction as dk equals to minus fk, k equal to 0, and dk equals to minus fk plus beta k dk minus 1 minus theta k wk minus 1. So what Kropetse did is, if you observe, if you go back to 7, you will see that 7 beta k defined by 7 is like a two-term parameter. The first part is starting from norm of dk minus 1 squared, and the other one starts from minus t on the other side. So Kropetse consider the first term defined in 7, and then they define it as their beta k. Here, just replacing g of xk, the gradient, with the capital F defined in problem 1. And that is going to give us equation 9. And they define another parameter, lambda k, by fk transpose wk minus 1 mu norm of wk minus 1 squared. So this lambda k is supposed to be theta k, given in H is a typo also. So lambda k should be theta k, not lambda k. That's the typo. So they define another parameter, lambda k, which is supposed to be theta k, this typo, by fk transpose wk minus 1 divided by mu norm of wk minus 1, where mu is greater than 1. Yk minus 1 is defined by this, and sk minus 1, wk minus 1 are given by 11. So if we observe now, initially the direction given when k is greater than 0 is two terms. You just have minus fk plus beta k dk minus 1. But in this case, an additional term is introduced, which is minus theta k wk minus 1 greater than 0, when k is greater than 0. Now, why is the introduction of this term? Now, the reason is this term is to introduce to achieve, most times, to achieve two properties which are very crucial in showing the convergence of any algorithms developed to solve problems such as one. One is this modification, or this term added, is normally introduced in order to establish that the direction is a distant direction. And that distant direction is very useful in showing the convergence of the algorithm. And another thing also very important is it helps in showing that the direction defined by A is bounded. And these two properties, the boundedness of the direction and the distancy of the direction, are very crucial in showing the convergence of the algorithm. So this term is not just introduced, but it is introduced in order to achieve these properties, which will help in showing that the algorithm converges. And another important is that it has been seen in so many literatures that this kind of conjugate gradient direction, which is in the form of three terms, it's most of the time it performs very good numerically. So these are the motivations behind adding this third term, and that is why we call the algorithm a three term. So our motivation is from the paper of Zeng and the paper by Kropetse and Kylo. If we observe in the paper of Kropetse and Kylo, they considered the parameter defined by 7 in the paper of Zeng and modified it to solve problem 1. Now, after reading the paper of Kropetse, I was opportune to review the paper. So after reviewing the paper, I observed that the second beta k defined by Zeng, I can also modify it and make it useful to solve problem 1 using the same, but not the same idea, using the idea of Kropetse, but not directly exactly the same idea, with a little modification. So the parameters beta k and lambda k, which is theta k given in 9 respectively, were defined so that the direction will be sufficiently distant and bounded. I have already explained this. And this was achieved by replacing yk minus 1 by wk minus 1. And the whole of this term, which is the third term in the definition of beta k given by 7 by Kropetse, by this term. So they replaced the whole of this term by this term in 7. And then in the other term, which they split into two. The first term of the beta k, they replace yk minus 1 with wk minus 1. And doing that, they achieve that the direction is sufficiently descent and bounded. Because to achieve the descent property and the boundedness, especially in unconstrained optimization problem, sometimes you need the line search. That is why I mentioned here, you remember, that the global convergence was established under strong Wolf line search. So without this strong Wolf line search, they may not be able to show the decency, the boundedness, and the convergence of the algorithm developed by Zeng and Zeng. But in our own case, we don't have this strong Wolf line search. So we have to think of another way of showing the decency, the boundedness, and the convergence of the algorithm. So that is why this term is introduced by Kropesi and Kylo in order to achieve that. Now, inspired by the work of Kropesi and Kylo, we now consider the beta k DHFDL given in 6 by Zeng and Zeng. And then we present a new conjugate gradient projection algorithm for solving one. The proposed start direction is defined as, now this is how we define it. We define it as minus f of xk if k is 0, and minus f of xk plus beta k dk minus 1 minus lambda k wk minus 1 when k is greater or equal to 1. And beta k is given by 13. Now this beta k given by 13 is exactly the first term of beta k of Zeng and Zeng here. This 6, you can see is the same thing. Right? We just replace g of xk with f of xk, because in our problem we have f. F is what we need if we are going to use the conjugate gradient method. So we replace g of x here with f. And another thing, if you observe in the denominator of this beta k, the first term of this beta k given by 6, the second term of the denominator is dk minus 1 transpose yk minus 1. So another thing we observe is that if we leave this as it is without changing yk to wk minus 1, just like Kropesi and Kylo did, we are not going to achieve our descent and boundedness property that we require. And hence, we cannot show that the algorithm converges, the sequence generated by the algorithm converges to the solution. So that is why here we replace yk with wk minus 1 in 13. You can see that, and replace g of xk by f of xk. And then we define lambda k the same way Kropesi and Kylo define their lambda k. Yk we define the same way sk, but wk, our wk differs from that of Kropesi and Kylo. Our wk is yk minus 1 plus tk minus 1 dk minus 1, where tk minus 1 is given as the 1 plus the max of these two parameters. Now, if you go back, you'll see that wk given by Kropesi and Kylo is just yk minus 1 plus dk minus 1. So our wk minus 1 is a generalization of that of Kropesi and Kylo. Because if you take tk to be 1, tk minus 1 to be 1 in our wk minus 1, you will see that this will going to be exactly that of Kropesi and Kylo. So our algorithm, our wk minus 1 generalizes that of Kropesi and Kylo when tk minus 1 is equal to 1 for all k. So now this is
about
yes.
5 minutes to go.
5 minutes? Okay.
Yeah.
Sorry. Okay. So let me summarize. So this is this modification helps us to show that the direction is descent and bounded. This is explanation of what we did, just replacing yk minus 1, wk minus 1, and this term by this term. And this dk minus 1 transpose wk minus denominator of the first term is shown to be greater than 0. And this property is what helps us to show the decency also. That is why we replace yk minus 1 with wk minus 1. Now, under these 4 assumptions, here is our algorithm. X naught in R is supposed to all in omega, as the case may be. Beta k greater than 0, and this. So in step 1, we check whether the stopping condition is satisfied. If not, we compute the direction in the next step 2. We compute a trial point zk equals to xk plus alpha k dk. where alpha k is defined by beta root to the power of I, where I is the smallest non-negative interval such that 19 is satisfied. If norm of f of zk is 0, then we stop, else we compute the next point by projecting by using the projection or projecting the previous point onto the convex set. And then we increase k by 1 and continue the process until the stopping condition is satisfied. Under those assumptions, we are able to show that this first lemma shows that the direction is descent. The second one is useful because we use in that lemma we are able to show that the norm of the function f of xk is bounded, f of zk also is bounded, xk is bounded. In this lemma we can show that. In this third lemma where we establish that the direction is bounded, and this lemma 4, which is very important, is used to establish a contradiction because the theorem 1 is proved using contradiction. So this lemma 4 helps in establishing that contradiction. So that is the importance of lemma 4. Next, I'm going to give the numerical experiment. So we call our algorithm new tree term, and we compare it with two algorithms by Gao et al., algorithm 2.1a and algorithm 2.1b. As I mentioned, the experiment is divided into two: one for solving nonlinear monotone equations and the other one for solving signal problems. Now, these are the parameters we choose. For algorithm, mu is 1.3, rho is 0.7, r is 0.01, and sigma is this. For algorithm 2.1 and 2.1b, the parameters come from the 7, the reference. We did not change, we use the same parameters they considered. And the stopping condition is when the norm of f of sk is less than 10 to the power of minus 5. We consider 5 dimensions, 6 initial points, and we consider 8 problems, which are here. Now, then we consider 3 metrics. The first one is number of iterations. The second one is CPU time, and the number of function evaluation. So in this graph, we can see that this graph is obtained using the Dolan and Moore performance profile. We can see that in summary of the Dolan and Moore performance profile is that the curve or the solver that lasts longer on the y-axis is the best solver. So we can see that the new tree term is the one that lasts longer on the y-axis. So which means that the new tree term is the best solver in terms of number of iterations, meaning the new tree term has less number of iterations in all the problems considered. In most of the problems considered, not all, maybe because it's not 100%. Here is for the time also. You can see that the new tree term is the best solver, meaning it has the less CPU time in most of the problems, almost 100%, more than 90% of the problems, it has less CPU time. And also for the function evaluation, you can see that it has over 60% success with less number of function evaluation. Now next is the application in signal recovery. Now I will summarize this. In signal recovery, actually problem 27 is what is being solved, but we can see that our algorithm is not solving a it's not solving a minimization problem, rather it is solving a nonlinear equation. So with the help of Figueredo and Xiao et al., they were able to show that that problem, that minimization problem is equivalent to this problem 30. And it was proved by Xiao that this problem 30 is actually continuous and monotone. And if you observe, this problem 30 looks like problem 1, f of z equal to 0, where f of z is defined as the minimum of z and hz plus c, where this minimum is component-wise minimum. So it means solving this problem is equivalent to solving the minimization problem. So hence, the algorithm for solving 1 can be used to solve problem 30, and by extension, it solves the problem, the minimization problem. So we consider reconstructing a sparse signal of length n from k observations. The recovery is assessed by the square mean of squared error, MSE, the original signal, where X bar is the original signal and X bar is the recovered signal. We choose the size of n to be 2 raised to the power of 12, A to be 2 raised to the power of 10. A is the random matrix generated in MATLAB using the command rand, and the measurement is distributed with noise, that is y equals to E x bar plus theta, where eta is the Gaussian noise distributed normally with mean 0 and variance 3 raised to the power. All these are inputted in the numerical experiment using the MATLAB software. Now, these are the parameters we choose for the new tree term. Beta is 1, sigma is 3 raised to the power minus 4. And we also compare this algorithm with two algorithms of Gao. In the paper by Gao, they call the algorithm 4.1a and 4.1b. And we use the parameters, the same parameters they considered in the paper. So we choose the merit function to be this f of x equal to be this much. And for fairness, we run the programs from the same initial point using the same parameter tau. And the starting point is x naught equals to E transpose y, and the stopping condition is given by this, where this fk is the function evaluation of f at xk. Now here is the summary of the experiment, one of the graphs. Now you can see that from this graph, at the top we have the original signal, and the second one is the noisy signal. So we consider the three algorithms to recover this noisy signal back to the original. You can see in the last three figures, all the algorithms we are able to recover the signal with the mean squared error given, the eta given, and the time given. But you can observe that in all the three metrics, which is the mean squared error and the iteration and the new tree term has the least error, it has the least number of iterations of recovery, and it has the least CPU time. So this makes the new tree term a very efficient method compared with some existing methods in solving nonlinear monotone equations and also in the signal recovery problems. So in conclusion, in this work, we derived a new tree term conjugate game method for solving nonlinear equations with complex constraints. The method satisfied the sufficient descent condition, and under appropriate assumption, the convergence of the rule method was obtained. We give numerical experiment to show clearly how effective the new tree term is compared to those proposed in some for the given constraint problems and also for the given signal recovery problems. So, which I mentioned in addition, the new tree term was also shown to be effective in signal recovery and also image restoration. I did not put the image here, but I have the experiment for also the image restoration problems. So thank you very much for your time and thank you for your attention. And here are some of the references. So thank you.
Okay, thank you very much, Auwal. Are there any questions from the audience?
Okay, Mr. Auwal.
Yes, sir.
Would you please go to slide 7, the slide number 7?
From here? I start counting
yes.
from here?
Yes. Slide number 7, where you mentioned the minimum of fx.
Okay, here.
Here you mentioned the unconstrained optimization problem of the minimum of fx, right?
Yes.
F is from Rn into R, but what does guarantee this that this minimum exists? You know what I mean?
Yes, I know.
So when you say unconstrained, I mean without any condition or constraint, I mean, what is the guarantee that this minimum exists? Because this minimum first must exist, then we are looking for it, right?
Yeah, exactly.
So what is the guarantee?
Because I I'm just giving like a summary of the work. Just
Mm-hmm.
if you observe in my own work also, before I move to the algorithm, I give some assumptions. Like in my first assumption, I said that the solution set is non-empty. So in the paper by Zeng and Zeng also, they assume that the minimum exists. Because
So
what
they assume that the minimum exists without any constraint or condition.
no, no, there are some conditions definitely, but because this is not the main work, this is just like I'm just giving where I got the motivation of my work,
I
and I
see.
just pick the areas I think are related to my work. I did not expand completely on the work of Zeng and Zeng because that is not
Mm-hmm.
my work. I only expand on those areas I think I was motivated by. But we all know that if you want to minimize the function, definitely the first order necessity condition and the second order sufficient condition has to satisfy. But that is analytic when you want to find the analytic solution. But in this case, they are trying to find an approximate minimum, not the exact minimum of the function. So
Oh, I
what they,
see.
yeah, it's an approximation, not exact. Even in our own problem,
Okay,
we are not finding the
approximate
exact.
minimum. And how do you define that approximate minimum? What is the definition? Okay, if in analytic, we know what it means, but how do you define that approximate minimum? What does it mean, approximate minimum?
Approximate minimum means like, in my own understanding, you you the initial idea is uh, you have a
Because
function.
when you say approximate minimum, it means we have some point we are comparing to do with that. Like there is something very close to that minimum, right? Then you call it
Yes,
approximate minimum.
yeah.
So again, to me, seems like
We are
that.
it's
Okay,
like they
okay,
are
go ahead.
trying because that is not my work. But what I understand is they are trying to find a point uh,
Mm-hmm.
whose difference from the
Mm-hmm.
exact has the least error. Because
I see.
definitely at the end, what the algorithm does is that you give a stopping condition that when this
I
happens,
see.
you stop. And at that stopping, the value of the function or the vector you got at that point will be your approximate solution, not necessarily the original. If it is possible, you may have it to be the original
Mm-hmm.
exact solution, but you are not sure whether it is the original. And
I see.
the reason behind this is most times because when dealing with very large scale problems, which
Mm-hmm.
you cannot compute manually to
Mm-hmm.
establish the exact solution. That is why
Mm-hmm.
the numerical approaches are introduced. And numerical approaches, we all know that it's very difficult to get exact solution using the
Mm-hmm.
numerical
Mm-hmm.
approaches. Definitely, there is going to be some
Okay, I
error.
understand this numerical.
Yeah,
Yes, of
yeah,
course.
yeah, yeah. So the error, we are trying to find the method that will give the minimal error.
Mm-hmm.
So
Mm-hmm.
in the paper by Zeng and Zeng, after introducing their algorithm, they have to compare with also existing algorithms and
Mm-hmm.
see whether their method is better in terms of
Mm-hmm.
error, in terms of iteration, in terms of the time to get the approximate minimum in that case with other
Mm-hmm.
existing algorithms. So that is
I see.
basically what they are doing. Yeah.
Okay, so the whole story is we do have some constraint under which the minimum exists, and then by some process we are approximating the minimum, right?
Exactly. Yeah.
Okay, okay, I
Approximate.
got it. Thank you.
In this case, I think it is approximate in the sense that the solution is almost critical.
Yeah, something like that.
Mm.
Something like that.
Hi, Dr. Auwal.
Yes.
Um, Dr. Auwal, I don't understand and the criteria of the convergence of your method. Could you please straight out about the convergence theory or something like that to confirm your algorithm, your methods converge to some point somewhere? Yeah, about the convergence.
Okay, about the convergence. Okay.
Yes.
I gave the summary here. The proofs are in the main work, but I give the summary. These are the lemmas. I said to establish the convergence of algorithm one, the following lemmas are of great importance. The first one is this lemma I mentioned. like I mentioned earlier, I said the whole idea of the modification, which I got the idea from the paper of Koropeti and Kylo, is to establish the descent property and boundedness of the direction. And that descent property and boundedness of direction helps in showing the convergence of the algorithm. So this first lemma shows that, or is telling us that the direction is sufficiently descent. One. The second lemma, in this lemma, because this is like a summary, this is not the only thing that is going to be proved in this lemma, that the limit of xk minus zk is 0. Also in this lemma, you can show that the sequence xk is bounded. The sequence f of xk is bounded. The sequence f of zk is bounded. And all these are also useful or helpful in showing the main theorem. Now the next lemma is telling us that the direction is bounded. So this boundedness also helps us in also showing that the sequence or the algorithm converges to the solution. I'm going to come to the theorem. I'm just giving the background now. Now this lemma 4, as I mentioned, we use it to establish contradiction, because this theorem 1 is established using contradiction. It's not proved directly, it's proved by contradiction. And this lemma 4 helps us in showing that contradiction. So what we do in the theorem is, we suppose that this lim inf as equals to infinity of norm of f of sk is not 0. So if it is not 0, by definition, we know that norm is always positive, so it means it's greater than 0. So if you assume it is greater than 0, along the way, you are going to come across, you use the descent property and you use this lemma 4 also, you are going to see that you are going to end up having a contradiction. So if you have a contradiction when lim inf of as equals to infinity of norm f is greater than 0 is giving you a contradiction, so it means the only option we have is that it has to be equal to 0. Now, if it is equal to 0, it has been proved in many literatures that if this lim inf as equals to infinity of norm f is 0, then you can establish that the sequence xk converges to the solution x bar or x star, as the case may be. But normally, because of tradition, we only establish the contradiction and we just neglect the other part, because it has been shown in so many literatures that once you have this lim inf as equals to infinity, you can establish that the sequence converges. So we only consider establishing the contradiction. So if the contradiction is established, so it means the other way around must happen. And if it happens, then the sequence will converge. So that is a brief summary of the convergence. I don't know if it is clear.
May I have a look about the assumption A1 until A4? Your assumption A1 to A4? Yes. You know, is the summation A2 F is monotone?
Yes.
If your F is not satisfied this case, can your method can still work?
It may work numerically, but theoretically, if you remove this assumption, F is monotone. That is
normally it's maybe not monotone. That's why I asked you about if F is not monotone, what happens? Your algorithm is still working on the right way or right time?
It will fail. Theoretically, it will fail because the monotonicity assumption plays a very, very important role in showing the convergence also. Example, in lemma 3, that lemma 3, in many places, you have to use the assumption that F is monotone to establish what you want. So once you remove this monotonicity, then definitely you are going to lose the convergence. So your method may fail. You may not have convergence.
And have you ever supposed the assumption to it failed to satisfy? I mean, you ever you try to make say F for A2 that's failed to satisfy. I mean, in the numerical experiments, have you ever tried about the F is not monotone and to see what happens?
I have never tried because I only consider the benchmark test problems, which has been used in so many literatures. And those benchmark test problems are already considered to be monotone. So I have never considered a general nonlinear equation to see what happens. So when I'm trying to solve this kind of problem, I only consider those benchmark problems that are already in literature, which are shown by existing literatures that they are monotone. So I have never considered looking for general nonlinear equation, which is not monotone, to see whether the algorithm will work or not. But as far as I know is that if you consider a function which is not monotone, then you are not sure. There's no guarantee that the method will work.
Yeah, I see.
Yeah, there's no guarantee.
Okay, that's fine. Thank you.
Thank you very much, Professor.
Or just a comment. I'm not sure the full detail, but in your assumption, if your capital F is a gradient of some convex function, then it is a convex. Then the capital F is a monotone operator. And when you assume that monotone operator to be Lipschitz continuous, then it implies that the function is strongly convex, and that implies your solution set is non-empty and unique, I think. So when your capital F is a gradient function, you have to be careful of the condition A1.
Okay. Because the problem is that we do assume that this capital F is the gradient of some function, small f. But the problem is that is just like a first order necessary condition. You are not sure about the second order sufficient condition.
No, but if
so
if F is convex, then it is also necessary. And the small f is necessarily convex because the capital F is monotone.
It's monotone. Okay, I understand what you are trying to say.
So you don't really need the.
We don't need assumption. We don't need the assumption A1 now because it's automatically non-empty.
I think so. If F is a gradient of convex function.
Okay, I will try to make a research on that to confirm. So that in that case we don't need to be putting the assumption A1. You can just keep it.
Okay, I have more questions. So could you go to the section where you study signal processing?
Okay.
Okay, here. Could you go to the next page? Or the, sorry, when you generate the matrix A.
The matrix, oh, the A, okay.
Yeah. Okay, here. I wonder where this matrix is used in your method, because I only see that you model your recovery problem with y equals to ex tilde plus eta. So where is A in your problem?
The A, Oh, okay, I understand. A should be E, sorry, it's a typo. It's E.
Okay, so A is E.
Yeah, it's a
So,
typo. Yeah,
okay.
yeah,
So your recovery matrix is E.
yeah, it's E, yeah. It's E, not A.
And you just generate this this matrix randomly by
using the command, the rand command in
so
MATLAB.
you use okay, so you have a specific distribution for this random matrix.
Yeah.
And
Yeah,
when
we
you
use
generate this, just any random matrix will work in your signal recovery problem.
Yeah, sometimes because normally we used to make the, we used to run the experiment for a number of times.
Okay, can you go to the next two pages?
Okay, this one.
Where you have your results. Okay, the next one.
Are you referring to this?
No, yeah. Okay, so from here you have the original one, which is not noisy, and then you
Not noisy.
you add the noise and some errors with the matrix E you generated.
Yes.
And then you recover it using the same matrix, or you generate different matrix.
I don't get the question. Can you repeat?
Okay, so you get the original signal, which is X, which is vector X.
Yeah.
And then you process it. And the measurements will be in a form of EX plus some noise.
Yes.
Yeah, where the matrix E here is randomly generated, right?
Yes.
And when you do the inverse problem, you use the same matrix E, or you generate a new matrix E for the recovery?
No, I think the same. But I will confirm, but I think the same. Because it's an inverse problem. I think it should be the same.
Okay. So I think you need to write it in a way that you fix the matrix E, because you just cannot generate a random matrix and recover any signal and retrieve the same result. I think so.
Okay, I understand what you mean, because the matrix is random. But I think
in practice, you don't know the matrix E. You don't know what
we don't know.
the measurement.
We don't know.
Yes,
we don't know.
I think the matrix E have to be chosen according to some distribution. For example, if you are working in image processing, then the matrix E have to be generated from some convolutional methods. I think in signal processing, the situation is similar. You cannot just generate a random matrix to recover in practice.
Yeah. Okay. I have to go back to the MATLAB code and study it very well again to see what is actually happening clearly, because the problem is I always have this problem. If the original code, actually the original MATLAB code is not done by me, so I just modified it. So there are some technicalities that I still find it difficult to understand.
Okay.
But I will keep exploring and see what I can get.
Okay.
Yeah, Dr. Auwal, one more question, please. Could you please show me about the graph of your result? The first graph of your result. Yeah, the first graph.
Okay, here.
Not this one. The other one. It looks like about the error graph. Yeah, no, not this one. Not this one. Could you please show me? Yeah. No. Before this, figure one. Not the previous one. Yeah, this one. Yeah, this one. Okay.
Okay, this one.
In the figure ones, if you see the pink line and the red line from the right-hand side, the graph we have seem to be converged to one, but the red one, your right-hand side graph, the red one, it's I am not sure about the behavior of this graph. The red one is maybe seem to be diverged. I would like to get your explanation about the result of this feature. Yeah, you know, the pink one is seem to be converged to be one, and for the right hand side, the red one is seem to be diverged.
I mentioned.
Auwal หายครับ
Well, you
Auwal, please share your screen again.
yeah, this one. Yeah. Could you please explain about the behavior of the red graph? It seems to be more than one. Dr. Auwal, can you hear me?
Auwal.
Dr. Auwal. Yeah. Okay.
Sorry, I think I have problem with my.
Yeah, don't worry. Carry on, please.
Okay, let me explain this.
The feature one, not this feature. The first feature one. Feature
okay,
one, not this feature. Yeah. Could you please explain about the behavior of the pink and blue graph?
Okay, this graph is obtained using the dollar and more performance profile. By the dollars and more performance profile is summary because it has so many steps. Is summary after plotting the graph, because you are using this graph to establish which is the best solver in terms of the metric you are considering. In particular, in this graph, the metric we consider is the number of iterations. So we want to know which of the solver, here we have 3 solvers. We want to know which of the solvers is the best in terms of number of iterations, meaning which of the solvers has the least number of iterations for the problems considered. Now, by the dollar more performance score is in summary, it says that you have solvers. So the solver that lie or that stays longer on the y-axis is the best solver. Now, if you look at the y-axis, it seems like a percentage, or like, yeah, more like a percentage. You can see 0.1 is like 10%, 0.2 is like 20%, and then 1 is like 100%. So what this graph is saying is, if you take the new 3-term solver, based on the problems considered, in terms of number of iteration, it has less number of iteration in over 80% of the problems considered. Because we considered 8 problems, with 5 dimensions with 6 initial points. So it's going to be like 8 times 5 times 6 problems. 8 times 5 is like 40, and 40 times 6 you have 240. So it's like you have 240 problems. And each time it's like you run the problems like 240 times. And each time you are going to report the number of iteration of each solver. So in this 240 times, the new 3-term algorithm has less number of iteration in 80% of those problems. So it's like in 200 problems, or in more than 200 problems, the new 3-term has less number of iterations. While the algorithm 2.1a and 2.1b have more than 20% of the problems considered. Now, somebody may ask, if you take more than 80% and more than 20%, it's going to be more than 100%. Why is that so? Because in some problems, they have like a tie. Maybe they have the same number of iterations in some problems. So in some problems, it's like a tie. So if it's a tie, it means you are going to have like an overlap. So you cannot have the sum of the 2 percentages to be exactly 100%, unless if at each iteration they have different iteration number, they have no similar. But in this case, if you have in some problems, they have the same number of iterations. If new 3-term has 2 iterations, maybe the rest problem also have 2 iterations. So in that case, they have it's like a tie. So that is how this graph actually works. But that does not show divergence. It's not divergent. Once it leaves the y-axis, then from the point it leaves the y-axis, it means that percentage is the number of percent the solver was successful in terms of the metric considered. In this case, which is the number of iterations.
Okay. You in this figure, you show about the algorithm 2.1a, but in this figure 1, I do not see about the result of algorithm 2.1a, where it is.
Oh, actually,
in this figure, it must be new 3-term and the algorithm of 2.1b, but I didn't see about the result of algorithm 2.1a.
Okay.
Where it is.
Actually, 2.1a is there, but the red one has covered the blue line because the red always overshadows.
Can you zoom in? Yes, it's maybe over in the red graph, I guess.
Yeah, it's under the red graph. In this for the number of iterations, both the two algorithms have similar performance. So that is why they lie on the same curve. And the red one overshadows the blue one, but it's there.
Really?
Look at, I don't know whether it's there.
With 2.1b?
Yeah, it's there.
Okay.
You can see it here. In this case, it appears because it's not the same. For the number of iterations, they are the same. So the red one actually covers the blue one, but it's there. But you can see in this one, because they are not the same in the CPU time, you can see the red one is there and the blue one is also there because they are not the same. But for this particular case, they are the same. Yeah, so that's why it covers it, but it's there. I don't know how I can zoom it. Maybe if I zoom it, maybe you can see. But if you look at it clearly, you will see that there is some element of blue in it at the edge.
Sorry, I didn't see. That's why I argue about the result of algorithm 2.1a, because I didn't see about the result. That's why I argue. Okay.
Yeah, it's there. It's there.
But okay, that is zoom out. That's why it seems to be the same graph. If you zoom in, it's a little bit different. Okay, that's fine. Okay. Thanks.
Oh, thank you.
Okay, any further questions from the audience?
Just a quick question. Why do you select to compare your result with only the work of Gauss, like algorithm 2.1 and B?
There are two reasons why I considered the algorithm of Gauss. One is because from experience, most of the time, if you send a paper for a peer review to a journal, we used to have this problem that they always ask us, why not consider a recent problem? Why considering an old algorithm? So because of that, I always try to consider recent algorithm. The algorithm of Gauss is 2019, it's published in 2019, which is quite recent. Yeah, so that is one of the reasons why I considered the algorithm of Gauss. And the second reason is that not all conjugate gradient algorithms for solving problem one are actually considered the signal recovery problem. But the paper of Gauss also considers signal recovery problems. So that is why I also use the problem of the paper of Gauss. So these are the two main reasons why I considered the paper by Gauss et al.
I see. Have you tried comparing with the work like the number 10 that you developed the algorithm from them?
Oh, the one by Kuropetse and Kylo?
Yes, yes.
Okay, the one by Kuropetse and Kylo, the reason why I did not consider comparing with is one, at the time I was working on this work, the paper of Kuropetse and Kylo was not yet published because I happened to be the reviewer of the paper. So I got the idea while reviewing the paper. And I rushed to do the work to avoid someone to do the work. So I was rushing, and at that time I considered that of Gauss et al. And another thing why I cannot compare with that of Kuropetse is because Kuropetse and Kylo considered unconstrained case. That is when omega is the whole of Rn. But in this, in my case, I considered a constrained case where the vector is obtained from omega subset of Rn, strictly subset of Rn. So I cannot compare my algorithm because my algorithm is constrained and that of Gauss is unconstrained. So that is why I did not compare. Yeah.
Okay.
Okay, any more questions? Okay, seems there's no more questions. Thank you, Auwal, for your
Thank you very much, Dr. Paris.
Okay, I will stop the recording now.